Hey everyone, it's Dr. Walker. Let's look at this example from v060C on rolling motion. In this example, we have a solid sphere of mass m and radius r, starts from rest, rolls down an incline. Find a translational speed v at the bottom of the incline. So we realize that this is an isolated system. The ball and the earth, there's no outside forces. We have conservation of energy. We can write it as the initial energies equal the final energy, so the rotational initial plus the kinetic initial plus the gravitational potential initial equals the final energies. Final rotational kinetic plus final kinetic plus final gravitational potential energy. When we have conservation of energy problems, we have to set the zero level. Let's set the ground level equal to 0. That's going to be the final position of the object. Now technically, it would be down here because we're looking at the motion of the center of mass, which is going from here to here. And then the initial position is going to be at a height h relative to our 0 position. Let's go ahead and cross out the terms equal to 0. When we start from rest, we don't have any initial kinetic energies. When we reach the bottom, we don't have any gravitational potential energy. Let's write down the terms that are left. We have mgy initial for the gravitational potential energy equals 1/2 I omega final squared plus 1/2 mv final squared. We're looking for Vf, but we know that the angular speed omega is related to Vf. We know that it's equal to V over R. So we do need to make that substitution. We also know the moment of inertia of our solid sphere, if you look at our table, is 2/5 mr squared. We can make that substitution as well. We can also make the substitution that the initial height is h. So let's see what we have. We have mgh equals 1/2 times 2/5 mr squared times Vf squared over r squared, that's r omega squared, plus 1/2 m, let's use capital M for the mass here, Vf squared. It looks like m is in each term, so we can cross it out. So the mass doesn't necessarily affect the speed, although the moment of inertia affects the speed because you see the factor of 2/5 is in here. In this term, here we can cross out the r squared as well. So let's see what we have left. We have gh equals 2/10 Vf squared plus 1/2 Vf squared. So gh, so 2/10 plus 5/10 equals 7/10 Vf squared. Now we can go ahead and solve for Vf. We're going to multiply by the reciprocal, so 10 over 7 gh to get rid of the 7/10, and then take the square root. So that is our final translational speed at the bottom of the incline, square root of 10 over 7 gh. And you'll see that if you have a different object rolling down the incline, you would just plug in a different moment of inertia, and that will affect the final speed.